Thank you so much, Michael. That was amazing. And indeed, anything in 3D becomes way harder. Like, I agree, I can't agree anymore that indeed anything in 3D can be a headache. But today we are here to um, showcase our work called LAPA, Look Around and Pay Attention, which is a work that's been done in Northeastern University in the Augmented Cognition Lab under the supervision of Professor Sarah Ostadabas and my amazing co-authors and collaborators in the lab. And today my name is Bishoy, and I'll be going through this amazing project that, as Harpreet said, we are grateful to announce that we have been awarded the Best Paper Award in 3DV 2026, and a huge shout out to my lab mate Shayda Moizi for representing the lab in Vancouver, Canada. And let's start. Let's step into the Lapaverse. So this is something I like compiled like half an hour ago. So I hope it works and I hope you like it, guys. So let's do it. So here you can see, guys, we have a frame of a Newton's cradle, which is a work that we have been doing in the EC lab regarding physics simulation and physical awareness and physical generation. But that's not the main story today. The main story, a lot of the existing work now, if they want to do point tracking for this specific example, the main go-to now is simply people doing 3D reconstruction via depth estimation, via colmap, via whatever, and then they try to point track these points in 3D and then reproject it into 2D or vice versa, which sometimes makes no sense to me because why would I need to reconstruct a whole scene, for example, to track one point? So let me ask something else. What would happen if I give you another perspective to this view? Would you be able to track better? Let's scale this a bit and say, what if I give you more views? And here comes our contribution. Instead of scaling the models and scaling the parameters and scaling the capabilities of the model, let's scale the views and do this. This is a real-time demo that happened today, half an hour ago. I compiled a bunch of pictures that we already collected, and I did some like LAPA. I did some LAPA on it, and this is just like some point tracking on it, and you can see the Newton's cradle from all views because our LAPA have access to these three views, and it could able. I'm sorry, I think the my laptop is not rendering this well, but if you like, if we zoom in, we can see the points, and as you can see, this is running on a 8 gigabytes GPU, and this is real time, and it can go up to a minute. So cool. So let's, before we get into our solution, let's frame the problem space. There are three families of prior work. Single camera trackers like Co-Tracker, Spatial Tracker V2 that are precise at the point level, but they are blind when a point goes out of frame or occlusion or even handling multiple views, but only at bounding box level. And then we have multi-camera object tracker that handle multiple views, but only on the bounding box level. They can tell you where a person is, not where their fingertip is. And we have multi-view correspondence method, match pixels across camera, but don't track over time. And because this is the gap, we can notice the gap right in the middle that nobody tried to figure it out so far. So, and that's exactly where LAPA sits, where it's the first method to fill this gap, combining point level precision, which is the point tracking domain, where with multi-camera point tracker, and the absence of any prior work here also meant that there were no dedicated benchmark. So we had also had to build one. We had to augment some benchmarks out of the existing ones, but we'll get into these shortly. So let me walk you through how LAPA actually work. The pipeline has 5 stages. I'll go through each one at a high level so you can get the full picture without getting lost in the math. There's not a lot of math actually, just like we're gonna cruise through it. So we'll start from the left to the right and we'll go through it one by one. And first, for each camera view, you can see here like view 3, view 1, view N. We need from each view, we run a point tracker, a mainstream point tracker, which is co-tracker 3 in our case. We get the 2D point trajectory within a sliding temporal window. At the same time, we pass each frame through a dyno 2, where it's a vision transformer. And I think Michael did an amazing job doing a quick recap for VITs. And this vision transformer is used to extract rich patch level appearance features for every tracked point. So imagine for each of these points being tracked, we get the surrounding patch and we get the features around it. And then so after this stage, we have 2D tracks plus appearance features. So we kind of have where these features are and how do these features look like throughout time per each camera view. And this is the main foundation that we build upon. Then next, we need to link those per view tracks into a shared 3D space. We start this journey by creating a normalized 3D volumetric grid that spans the scene. Think of it as a 3D canvas, and then we project every voxel of that grid into each camera view using a calibrated intrinsic. And just to get it out of the way, this is the limitation of LAPA so far, that we need to use camera calibration. And this is how you can see like the voxel. And this is actually a rendered volumetric attention. And essentially the model is trying to pinpoint where is this corresponding point per camera view in this attention grid. So think of it this way. We want to be able to correspond all the points that they are getting tracked in 2D, but in this 3D canvas, I'm trying to correspond it per each view. So we have camera view pairs, and we're trying to correspond with it. Then we aggregate these features from all the views into that volumetric grid that you're seeing, and this is exactly how LAPA is seeing the view. And each voxel collects a weighted contribution from tracked 2D points across every camera. The result is a 3D volume that integrates a 3D feature space that integrates everything that all camera sees in a shared view or in a shared space. Crucially, when a point disappears from one camera, and this is where I think our method shines. So when a point disappears from one camera, the other cameras can still contribute. So nothing is truly lost throughout the scene. So, and then here's the core innovation, or where we actually tried a bunch of stuff, and we tried a lot of stuff in order to pinpoint, and maybe we can add to Michael's lessons. So this can be lesson number 6. So here's the core innovation. Instead of computing attention via dot products or between vector feature vectors, which is the standard approach, but we use spatial distance because when you think about it this way, if you are seeing something from a bird's view or a top view, you kind of try to associate things with distance. Because if I'm telling you, like, if this chair is closer to the table, you will probably associate closer to the table throughout all views. And it's like an anchor point or an anchor feature. So we use spatial distance for each voxel in the grid. We project it into the camera view and compute its Euclidean distance to every track 2D point. So imagine you have like this like spanning distance, Euclidean distance from each track point. And the closer the point, get higher attention via softmax of over the negative square distances. And this is where the learnable temperature controls how sharp the focus is. And you can go back to this volumetric grid, and you can actually see these points getting like, because you can see here the Euclidean distance and we're going to get into the geometric mask, and you can imagine how would the model be able to associate these points via just distance. And I think this is amazing that similarities you can use. Essentially you can say that the primary signal for the attention is spatial distance rather than feature similarity. And it actually, this was the main thing. And you will see in the ablation feature, in the ablation studies, how just turning off and on the spatial distances will make a huge difference. And it's simply fully differentiable, and it's implicitly encodes epipolar geometry without any hard constraints. So adding this epipolar geometry through the camera views will give us this beautiful either epipolar attention mask or SFM, which is structure for motion, from motion. So here, I'm sorry, we had to go through some math. This is the only equation with three. Actually, there's another equation, but this is the main equation we'll see. And in this, like in this slide, we just show the attention formula in detail, and like we try to let's go. It's just like color coded. So the key intuition: a point near an epipolar line will naturally have a smaller Euclidean distance to the projected grid voxel. So it gets a high attention automatically. So there is no need to hard code any epipolar constraints, and the geometry emerges from the distance computation. We do then optionally reinforce this with explicit geometric match with masks, which bring us to the next slide. So we enhance the epipolar geometry encoding with either epipolar or structured from motion constraints through the attention masking. So let's go back one more time. So the attention matrix is just like the projected grid and the detected points, and we do the Euclidean distance, which is this. And then we have the learnable temperature over with the softmax that we talked about. And then we use the geometric constraints to reinforce this. So if we take this and encapsulate it, now we have a feature-rich 3D volume. We need to turn it into an actual 3D point position. This is all cool, but we still need to relocate these points into 3D, because all what we have in this like cool looking 3D grid, or like whatever this point, like this cloud of attention in 3D, we need to actually use this grid to pinpoint these points in 3D. So we use the track queries we started with, because you need some track queries, which is like the initial point grids. And with the learned feature vectors, one per track point, that are matched against the volumetric representation using some cosine similarity. And then these queries are initialized at the first frame and updated via momentum. So they carry the points identity through time. We also fuse the camera calibration, which we said this is the limitation so far. And I think we're trying to work this in our future work. So we fuse the camera calibration info and the 2D track features that we got from the initial step with the dyno and the VIT to give the model every possible cue. So we're trying to give all the hints available to the model to be able to track these points. And then in the final step, instead of using the classical direct linear transform triangulation, which is like adopted by most of the 3D tracking or 3D reconstruction, we use actually a small MLP from just 4 connected layers to predict the 3D coordinates directly from our compound feature. And you can actually think of it that this is a reconstruction, but it's a 3D reconstruction via triangulation, but not like the conventional triangulation. It's just like you take all these features and you try to like estimate the 3D position of these points in 3D space. And this is fully differentiable, and it handles uncertainty, partial observation, as we talked, like, for example, if a point disappears from one view, the model will be able to estimate its position from the other views. And the whole pipeline is trained end to end, which is a big advantage because we don't need to stage the training from, for example, a lot of like the other methods, they need to do the depth estimation and then they have to go through the reconstruction and then the triangulation, but this is all done end to end. And then, yeah, so we have our 3 loss terms are actually simple and straightforward. We have the projection loss, which ensures that the predicted 3D points are reprojected back into 2D space correctly into each camera view. So this is a nice take because it was so nice for us to take this 3D trajectories and then compute it back into 2D space and see if they align with the correct view or the correct position. And then the attention loss encourages the strong cross-view correspondence between the matching points. So essentially, we're trying to force the model to have the highest attention between, or that like having the highest attention through the correspondence between each camera pairs, or like the camera pairs. And yeah, so all the three losses are trying to train the model end to end. So the experimental setup is also straightforward and been done a lot of times. So we use two benchmarks. We have the tab with 3D, which is the panoptic subset, and then we have the point odyssey, which is the robot subset. And you can see that we added an MC next to it, which is used to highlight this is the new benchmark. So we took these two data sets and we used their camera calibration with their track queries to do camera correspondence or like point cam to do point correspondence between camera views to ensure that we have the right ground truth. And we again we had to do a lot of like manual like corrections and like audit everything again to make sure that they are actually correct in 3D space. Um, yeah, so we modified the generation pipeline to output per camera calibration data alongside the rendered sequences. So both data sets feature challenging occlusion and complex motion, which is exactly what we try to showcase our method. So the numbers, we can go through the numbers. So the evaluation metrics, I'll go through them really quickly. We have EPD, which is the average position detection accuracy, which measures the 3D point localization accuracy. We have the occlusion accuracy, which evaluates the recovery after occlusion events. We have the 3D average Jacquards, which is the overall 3D tracking quality over time, and the 2D average records, which is the consistency of projected tracks across camera views, which corresponds with one of our loss functions. So on tab with 3D multi-camera, LAPA achieved 37.5% on EPD compared to the next best model, which is 32. On Point Odyssey, we hit the 90.3 actually on EPD and 3D AJ of 0.95. And what's amazing about LAPA, as you saw in the beginning of the presentation, it was running on like a laptop on real time, and it can run at 39 FPX on an RTX Titan hardware without needing any separate depth estimation because we took the depth estimation out of the equation. So there's no bottleneck compared to like track on and co-tracker that they need some depth estimation to be able to do the 3D point tracking task. So we're like, if we gonna put like this into one sentence, I think we are simultaneously more accurate and we are 3 to 4 times faster than depth-dependent approach, which I think is really nice. Especially I remember when I first tried Spatial Tracker V2, because this was the first method that was actually impressive enough to grab my attention on how it can take a 2D scene and project 3D point tracks. But I remember because I tried to run it on I think 300 frames, 300 frames a sequence, and I don't know, I got like the famous CUDA out of memory error saying like it requires, I think, 90 plus gigabytes of VRAM, and I said, yeah, that's not gonna work. This is the full comparison table. Every single camera method is outperformed by a wide margin on both data sets. The biggest gaps show up in 3D AG in the occlusion and occlusion accuracy, which makes sense since those are exactly the scenarios where multi-view information helps the most, and especially when you have access to more camera views instead of reconstructing scenes and basing your estimation on an estimate. So yeah. So it's worth noting that Spatial Tracker V2 and Tap BIP 3D are the closest competitors, but at the end of the day, they run only at 3 to 5 FPS because they're heavy reconstruction pipelines, while LAPA is completely real time. And Here are the qualitative results. You can see the basketball getting tracked, and one of the highlights of this scene that this subject got out completely of the frame, but as you can see, it's the subject is appearing in this view and this view as well. So in the 3D domain, or like the LAPA verse, you can see the full reconstruction without getting any point loss. You can see all the points are getting shown. We can also show different results. These results are from the CMU panoptic datasets. So you can see how we are tracking them through time and space. Um, This is an interactive demo and how we can actually use this for more IO based things. So for example, if you have view one, view two, view three, and a user actually picks a point in view one, and this is where things gets actually interesting, because when you think about it, LAPA can now reproject points accurately. So what you can do is you can say show in other views, and using the cross-view correspondence, you can actually do accurate reprojections back in the two views, and then start tracking in 3D. You will see that the model is tracking exactly the 3 points in 3D as well as in 2D. As you can see, like this point is occluded, but still both tracked in 3D and 2D. This work is funded by NSF and Northeastern University, and this is the project page. Please go there and check our work, and yeah, and I'm happy to take all your questions. Thank you.
Hi, Bishoy. Thank you so much for your talk. I have a couple questions here, a few of them actually. One is for the point tracking. How is the point on the 3D object selected?
Say again. I'm sorry.
Yeah, the question here was for point tracking, how
Mhm.
is the point on the 3D object
Uh,
selected?
yeah, I think I'm gonna, like, we have some backup slides here, and I like to use them to explain this. This is interesting because this is again the same question we get everywhere we showcase our work. So in 3D, you don't choose the points. You choose them in 2D, and there are two ways to choose them. You can either choose them by like saying I'm gonna track all the grid. So you put a full grid of points, and through time, all the points are getting tracked. But I know in the visualization, everyone was gonna say, oh, but these are the only ones getting tracked. How do you do this? So in the tab vid data set, you can actually choose which points, and the points that are getting tracked in the data set are actually chosen by the original contributors of these data sets, that they choose the you can say the dynamic objects, and this is how we train our model. But in fact, the model get trained on full grid, but we don't choose the points on the 3D. We start by the 2D, and then we go into 3D.
Next question is how much is compute benefited compared to traditional 3D
Yes.
reconstruction?
Yes. Let me check if we have a backup slide. Oh, no, we don't. So essentially, if you use this table, so compared to spatial tracker, I think LAPA, if it's working with 3D with three views, we use up until like 8 GB. And compared to spatial tracker that is only getting one view, but still needs to do reconstruction, it needs up to 48 GB. So 12 to 48, so 3 to 5 times or 3 to 4 times.
Next question is our position, this is coming from MH Tam here in the audience, are position encodings included as the input to the geometric attention layer?
Yeah, that's a really cool question. So in our pipeline, oh, sorry. So here we actually don't encode the positions. So the positions are only through the XY. So the model is position encoding agnostic. It doesn't care where's the point, as long, because think about it this way. you only need the distance between the epipolar line. But I remember we wanted to add track ID encoding. So we don't encode the position, but we encode the track ID. So for example, when you start with the track queries, so for example, I think you can see it if you zoom really much here, but you can see, for example, this thread point has ID 0. And this is how we identify these points because throughout the tracking sequence, I'll try to make this track ID 0 no matter what. So we don't encode the track position, we encode the track ID or the track query, which is given in the benchmark, by the way. In the benchmark, they have a track ID or the track query for each point on the 3D view.
And then the second part of MH10's question here, are the cameras weighted if the same point is captured on more than one camera?
No, no, no. This is also a really good question, but we thought about it, but we thought that it's going to be too much heavy lifting for the model to think about. And I think it's better just to let the model be able to reason through these features because essentially we encode this in the geometric mask or the geometric attention because here, in the epipolar, you can see that the epipolar distance can encode this or can weight this. Because if you think about it, if each camera is shooting out rays and you can calculate the distance of the point through the epipolar line, the closer they are, the higher the weight. So instead of doing this explicitly, it's done implicitly through the epipolar distance weights or the attention weights, but not camera based. It's more because what happens if we scale up or scale down? We didn't want to play around too much with this weighing or camera weighing.
And then a question here also has to do with cameras. How does this scale with the number of cameras?
Yeah.
Attention costs
Ooh.
can grow fast. So what's the practical ceiling? 4, 16, 100 plus?
Yeah, that's an amazing question. So here, I I don't think so we didn't add the performance or if anyone wants to check the paper, we have a detailed table for this. But so so we actually there's two things to think about. Um, the grid size, because the grid size that we use is 16 by 16 by 16. And when you think about it, yes, it increases dramatically and it increases so quickly. So that's why I think the 24 by 24 was the highest one we tried. But when we tried 32 by 32, we were hitting out of memory so quickly. So it does scale really quickly. And I think it scales 4 times because here's the thing, the attention matrix or the attention grid scales up the memory, but it doesn't touch the parameters or the flops needed to compute it. So that was the good thing because um, we didn't have to worry about it because it's the same operations needed, whether it's grid size 8, 16, or 24. But then when you go back to the cameras, here when things get a bit weird. Yes, you can keep increasing the cameras and the attention will grow with you, but you have to take into account that we can play around with the grid size as well. So you can do 4 cameras, but with like 8 by 8 by 8, or you can do 5 cameras and 16 by 16. So this is where we played with the uh, sizing of the number of cameras and the size of the grid.
And another question here, is there a limitation on the number of views required? If the multiple views, if only partially captured the object, will the 3D point tracking still work on the point that's visible?
Yes, that's also a great question because as you can see in this ablation table, if you keep increasing the cameras, it doesn't help as much as you think because yeah, sometimes when you have a lot of overlapping views, it just keeps adding a lot of points to be computed. And because the soft attention won't give you better correspondence, so 3 cameras was the optimum. 3 cameras with 16 by 16 by 16 was the best configuration we tried.
And while we're on this topic of the compute and all that, which GPU did you end up using for
Yeah,
this?
so for the training, we use the V100, and again, so again, in you can people can refer to the paper, but this is also a really good thing to talk about. So in the high-end hardware, which we tried was V100 or better, you can scale up from there, and the V100 we use was 32 gigabytes. And with three cameras and 16 by 16, it can run up to 55 FPS on, and it would have 37.5 EPD. On consumer hardware, which is an RTX Titan or similar, LAPA can work with two to three cameras and 16 by 16 and still hit the 39 FPS. But also in the resource constrained environment, which is the demo we saw in the beginning, was I think like a laptop or something can be used with three to four cameras, and it still can hit like the 60 FPS, but you will have lower accuracy as you saw. Because I think in this view, I use like an 8 by 8 by 8 grid size.
All right. A couple of the questions here. First question is the project page. If whoever's asking that question, if you look in the chat right now, there are links right there to the paper, the code, and the project page. So you can find that there. Um, the last question I'll ask, and then there's one more in the QA. If you want to type out the answer, you can do that. But the question
Sure.
here is, what is it trained on, and how do you get ground truth 3D point trajectories
Yep.
at scale, especially through occlusions?
Yeah, so I think we mentioned that, but let's do it again because again, this is a repetitive question that we always get. So we use the Point Odyssey. I mean, the Point Odyssey is a great data set to use, and again, because these so in the TabVid 3D, for example, you have like 3D points, and you have so what we did is in the TabVid 3D, you have one view, but you have 3D points. Okay. But because these, like the contributors of these data sets, they use the CMU panoptic data sets. So we meshed them together. We went back to the CMU data sets and we used all the views. And since you have ground truth in 3D, you can use the track point IDs through these points and connect them together. So again, I think again, it says like what we did is we established the mapping between the original CMU panoptic data set and the multi-view setup, and the camera calibration files, they matched perfectly from the TabVid 3D and the CMU panoptic, and when you mesh them together, you can essentially project back the 2D points into 2D. Similarly with the Point Odyssey.